Hello everyone. I've decided to do my final project by teaching a reinforcement learning agent how to play the game Rocket League. Rocket League is best described as soccer with cars. As you can see, the environment we're in is an enclosed arena with a ball at the center here and any number of cars. We're in a sandbox environment, so it's only going to be just one player. The action space consists of continuous actions, which are throttling, steering. You can also perform jumps. You can apply boost. You can also drift the car by sliding. You can also get into the air and change your angular rotations. You can string together any of these combinations, which allows you to create a very nice environment to test out different reinforcement learning techniques. The complexity of this game essentially arises from your ability to have a continuous action space and your ability to perform actions simultaneously. So here's the methods that we're going to use to solve our problem. We actually have to ignore DQ1 for this because DQ1 assumes independent and discrete actions. Since we have continuous action space, we assume the policy is a continuous function. And since the policy is continuous, it is therefore presumed to be differentiable, meaning that you can use any gradient-based optimization method, such as gradient ascent or gradient descent, which are used in neural networks to approximate the policy function. What that means is that we can split off DQN into two separate networks, one which learns a Q function for the given state in action, and one that learns essentially the policy, which are respectively called the critic and actor networks. And this method is called DDPG, which is a deep deterministic policy gradient. It is a modification of DQN applied to continuous action spaces. So let's start off with the first experiment that I ran. The reward function for this model is the Leo distance reward function. And what that is a normalized distance that is an exponential raised to the power of a distance divided by the maximum attainable velocity of the car. And so if the distance is 0, that means the player and the ball are in the same exact spot in space, therefore minimum distance can't be negative, and e to the 0 is always 1, so therefore it is normalized. Now the expectation of this model is not that we get anything interesting out of it, but we really just want to see that the model is able to actually move the car towards the ball. Okay, so let's see what this model learns. Okay, so here we are in the environment. So I'm using the ball cam. It just ensures that we keep the ball in frame instead of looking at the direction the car is traveling in. So in this case, we saw that the car started at one of the kickoff positions and it shot past the ball, and it just seems to be being confused about what to do next. The reward is that if you get close to the ball, we get a larger reward, so it's definitely not maximizing the reward in this case, but it does show that we are going in the direction of the ball in some cases. So we can see that this model at least proves to us that we can train within a reasonable time frame. So let's move on to the second experiment. We want the model to actually start learning how to play the game. And so the purpose now is to be able to score a goal. So what we've done is change the reward function from the Leo distance to the ball to goal velocity. And what that means is that we have a vector g. G points us into the direction from the ball to the goal. And we have a vector v, which is the linear velocity of the ball. In order to maximize this reward, we want to maximize the projection of the velocity vector onto vector g. And so that means we just have to take the dot product of it, and both should be normalized. Now what this means is that in order to maximize the reward, we have to hit the ball in the direction of the goal as fast as we can. Now hopefully that should be putting us in the right direction of where to go in order to train further models. So let's see what this model has learned. So here we are in the environment. I trained this model with 1,000,000 time steps. It may seem like a lot, but in the complexity of this game, it's technically not really all that much because it has to learn a lot of complex actions. So now what you just saw here was that off kickoff, we saw that the car went straight for the ball, and it went really fast speed, so I would say. So it definitely knows that it has to hit the ball with maximal speed of the car in order to maximize the reward. It missed in that case, but now here we see an example where the ball was actually hit towards the goal, not necessarily into it, but we do have a velocity vector component in the direction of the goal, therefore we would have received a positive reward. Now, as you can see, there's some confusion of the vehicle right now, because after it hit the ball, it was not able to, and it's scored here, after it hit the ball in the last episode, it wasn't able to actually go chase that rebound and try to hit it again. So it seems like what this model is learning in this case is that it's learning to go to the center position rather than towards the ball. And making course adjustments really, ooh, that was interesting. It's able to make course adjustments here. So it definitely knows the angle to hit at. As you can see, it's actually scoring, so it's accomplishing one of the things that you're supposed to be doing in this game. So now we have to train a model with the correction that the car must know that it must chase the ball wherever the ball is on the field. So let's go into this third experiment here. I've changed the initial state of each episode. The ball and the car are both put into random positions and are given a random velocity. Now hopefully that should help us learn to be able to go to any position in the field and chase the ball. The reward function is also changed in this case. And instead of giving a positive reward, like we did for the Leo distance, we're actually converting the distance reward into a penalty, meaning that if the player is further away from the ball, it is penalized. And if it's closer to the ball, we minimize that penalty. For a positive reward, we're taking this velocity and distance dot product. And so what this means is that this velocity vector here, v, is the linear velocity of the car. And what we're trying to do is we're incentivizing it to move as fast as it can into the direction of the ball. So hopefully this should mean that this reward function incentivizes the car to chase the ball. So let's see what this model is able to accomplish. So here now I've started the game, and now we're waiting for the environment to be generated. So once this countdown expires, we'll see the environment reset, and we see that the ball and car are both in random position in the field, and we see that the car is now chasing the ball. So that's as expected. So good, we're following what we wanted to do. One of the things that's happening here is that we're moving away from the ball a little bit, but what that allows the vehicle to do is that it's now able to get some distance between that and the ball and accelerate to build up the velocity. So while we are incurring a distance penalty by moving away, we're actually able to offset that penalty by increasing the speed of the ball. The player. So what's happening now in this example here is that we're staying as close to the ball as possible, but the car is trying to match the speed of the ball so it doesn't push it away. What this essentially equates to is dribbling. This behavior was not explicitly taught to the player, but it was able to pick it up based off the reward function. Before we go to the next experiment, I have to go back to this reward function really quickly. Early on in my experiment, I had accidentally changed the direction of this distance vector from player to ball to player. And what that means is that this dot product here would have its sign flipped, meaning that if the player was moving towards the ball, it would receive a negative reward. If the player was moving away from the ball, it would receive a positive reward. Now, the issue is that we still have this distance penalty D here. And so that means if the player was away from the ball, moving toward it would incur an even bigger penalty. So when we have two incompatible reward components, how does the model learn to maximize the reward? This one will be interesting, so let's see what happens. So now that we're back in the game, let's see what happens with this model. Initially you can see that the car is moving towards the ball, so it's definitely trying to minimize that distance penalty first. The interesting thing that you're going to see here in one of these episodes is that the car is now leading the ball, meaning that it's moving in the direction that the ball is moving. So it gets in front of the ball and it tries to maintain a distance away from it while matching the speed of the ball. Or in some cases it actually moves faster away, but usually, as you can see here, it's trying to match the speed of the ball in the direction that the ball is moving. So by staying close to the ball, it's minimizing a distance penalty, and then moving the direction that the ball is moving, it's able to maximize the velocity component. So this is not something that we would have ever been able to predict occurring. So this is definitely one of the more interesting examples of learned behavior for different kinds of reward functions. So let's move on to the final experiment. This experiment will take everything we learned from the second model and the third model. It's similar to the third model, where we start with a random position and random velocities of each object in the arena, and we also keep that distance penalty to incentivize the car to stay near the ball. But instead of measuring the velocity and distance between player and ball to incentivize the player to hit the ball, instead we're going to incentivize the player to hit the ball towards the goal, like we did in the second model, where we're taking the projection of the velocity vector onto the ball to goal vector. Hopefully this should be enough for the player to learn how to find the ball anywhere in the arena and hit the ball towards the goal. So let's see what this is able to do. So now we're back in the environment. Let's see what this model has learned. I've been observing it for a little while, and I've been recording some of the actions it's been taking. So what you're going to see here is that consistently the model puts itself in a good position to actually do something. It doesn't always take action that would lead to a score, but if any human player were to take control from that point on, you'd probably result in a score, or at least put yourself in a good position to score. We always chase the ball, and it seems to always put the ball between itself and the objective goal, which is a good thing. It's actively learning how to play, and it's definitely playing in the spirit of the game. You'll see that this model, I trained it for about 5 million time steps. It takes the whole night to train on my machine, but the car has started to adapt and utilize some of the mechanics more efficiently, such as slide, in which case that example you just saw here, it was able to slide and turn quickly to face the ball, and then it used boost to speed up that turn. You'll also see some cases where the car jumps to put itself in a position behind the ball, which is interesting. Not an efficient use of jump, but it's definitely more controlled than earlier models, which is progress, I would say. I would not use this model as a bot yet. We still gotta learn some better strategies, but I would say for now it does what it's meant to do. It's trying to score, it's trying to play, and it intentionally scores. I wouldn't say that there are accidental positive scores. that this model does. If the ball is going towards the goal, it does not interrupt the trajectory of the ball. And if the ball is not going towards the goal, it tries to put itself in a position to score, though it may not always. So I would say mission accomplished in this case. We're able to show that using a DDPG model, we're able to approximate the continuous action space, and the model is able to take simultaneous actions, and it's able to actually learn an open environment such as this.